Okay, so welcome to the third video in which we're just discussing limits in the L infinity space. So in this video I just want to firstly give you a bit more intuition for what pointwise convergence of a sequence of sequence means, and also I want to introduce the terminology uniform convergence for convergence in the D infinity metric. So let's say we have a sequence of sequences. So let's say S is a sequence of sequences. So we've got S1, S2, S3, S4, etc. And these are all sequences in L infinity. So they're all bounded sequences. So Si are all in L infinity. Okay, and we're going to say that this actually I won't say it converges to L because that's what the point of this discussion is. Let's write out what these sequences are just to keep ourselves clear of what they are. So S1, S2, S3, these are actually equal to sequences themselves. So this is the first sequence. We put the superscript to denote the that it's the first sequence, and then the subscript is going to denote the term that it represents. So X11, X12, X13, etc. And S2 is equal to X21, X22, X23, etc. And S3 is then equal to X31, X32, X33, etc. And obviously we would go on this way, and we'd also go on this way, so we'd have S4 and S5, etc. And you'd go on. Right, and we described pointwise convergence as you split this sequence of sequences up, and you say, okay, we're going to construct some sequences of real numbers from this problem, and the way we're going to construct a sequence of real numbers is we're just going to take the first terms of each sequence. So we're going to construct a new sequence, which is just the sequence of all first terms of these sequences. So basically, if you want the first term of this pink sequence, it's going to be the first term of the first sequence. So that's X11. Then the second term of this sequence is going to be the first term of the second sequence. So it's going to be X21. The third term of this sequence is going to be the first term of the third sequence. So X31, etc. And this might have a limit. So if this has a limit, we'll say it converges to L1, and then what we can do is build a new sequence, and this sequence, the terms can be the limits of these sequences of each of the terms, basically. So L1 is the limit of this sequence of the first terms of all of these sequences. But of course we could build another sequence. We could build, let's say, sequence green, which is the sequence we make from all the second terms of the sequence. So if we want the first term of this green sequence, I'll put green here. If we want the first term of this green sequence, it's going to be the second term of the first sequence. So we go to the first sequence here, we say, what's its second term? So that's X12. Then we go to the second sequence, we say, what's its second term? That's X22. And then we go to the third sequence, we say, what's its second term? And we say, that's X32. And we go on like that. And we can basically go as far as we want. We can go to the ith terms of each sequences and build another sequence of the ith terms of the sequences. So if we want the ith terms, then we can build a sequence out of the ith terms. So we can build x1i, x2i, x3i, etc. And you go on and on and on. So for arbitrary terms, you can build these sequences. Now, if this sequence of sequences converges pointwise, it means that each one of these sequences of all the terms of these original sequences converges to a limit. So let's say the sequence of second terms converges to L2, and the sequence of the ith terms converges to Li. So we can then construct a new sequence, which is L1, L2, etc., all the way on to Li, and you go on past that. So another infinite sequence. And this sequence of sequences is said to converge pointwise, or you could say termwise, to this sequence down here, pointwise/termwise convergence. And I just want to give you a bit more intuition for why that is called pointwise convergence, termwise or /termwise convergence. Termwise is probably a better name for it when viewed like this, but I'll show you why it's often called pointwise convergence. So, if we can view these sequences S1, S2, S3, S4 in a different way, basically, we can view them as functions. So let's plot basically this sequence S1 as a function, and it maps basically all the natural numbers, so 1, 2, 3, 4, 5, etc. It maps all of those onto a real or complex number. So we're imagining, so that we can draw it easily, we'll imagine that it's real numbers. If it's complex numbers, again, it's the same idea. You just ascribe a complex number to each natural number rather than a real number. So what we're plotting is the graph representation of the sequence S1. So the sequence S1 ascribes to 1, the first term of this sequence is x11, so that's just going to ascribe some number x11 to the first term. Then to the second term, the second number, so to 2, we are going to ascribe x12. So this is how you can view a sequence as being a graph. Of course, it's not defined on all the real numbers, it's only defined on a subset of the real numbers, which is the natural numbers. Okay, then we've got x13, let's say that goes up here, x14, and did we plot 5? Yeah, we'll have that then as well, x15. Okay, so I'm going to highlight these points as being, what colour should I call them? Let's have them as blue. So S1, I'm going to make blue basically. So all of these points are the points corresponding to S1, okay? Now, obviously it would go on. It would go on for all natural numbers. You would ascribe a real number to it, and you describe the appropriate term, the corresponding term of the sequence. Now, let's plot on S2. So let's give S2 orange colour. So here's orange. Right, so let's put on the points of S2. So to 1, you're going to ascribe x21. To 2, you're going to ascribe x22. To 3, you're going to ascribe x23, and I'm just drawing these points arbitrarily. They're just arbitrary points. They don't need to be. This one, I've drawn them all below the blue point, so I'm going to draw this one above it. So x2. Wait, what have I done there? That should have been 4. This should have been 5. So let's just highlight those all up, and basically, right. So let me just finish the drawing. Basically, you're going to continue plotting, or you could continue plotting and you could plot S3, S4, etc. You could plot them all as functions. And then basically what we're doing when we take these term-wise or point-wise limits, when we take the limit of this sequence of first terms, what we're actually doing is taking the limit of this sequence of points that have been mapped on, of this sequence of points basically here, that are the points where 1 was mapped onto. So this is basically all the first term. So let's say it appears something like this, and you get all these points and it converges down to something. That's why this is called pointwise convergence, because it's converging for the point. It's converging to L1 for the point 1. So let's say this is L1 down here. Okay, so I'll give that another colour as well. I'll call that green. So we'll call the eventual sequence L. We'll call that green. So equivalently, on all the other points, that we've said that these are all converging. That these are all converging to these points here. So to this sequence of values here. So the ith sequence of the sequence of ith terms converges to Li down here. So all of these are going to be basically convergent sequences converging to some value. So this is L2, converge down, let's say, to L3 down here. Okay, etc. So that is why it's called pointwise convergence, because basically all of if you view these sequences as functions, then at every single point, as you let the sequences go to infinity, all of the points are converging. All of the value of the function, the value of these converging functions, is converging to a point. It's converging to a number at each point. They are not necessarily converging at the same rate, though, is important to know. But as you let this go to infinity, as you let these functions go on and on and on, they do get closer and closer to this function L, or this sequence L, whatever you want to see it as. But that concept of, for each of these terms, for each of these points, if you pick a point, so like 1, 2, 3, if you pick an individual point, then the notion of pointwise convergence is, if you pick an individual point and you look at what that point is mapped onto by this sequence of functions, then that sequence of real numbers is converging to some value. That's what pointwise convergence means. So that's a better sort of intuition for why it's called that. And it's quite nice, in my opinion, to see sequences as being these functions. It gives you an easier way of visualizing this, what it means for these sequences to converge potentially, than just seeing them written out like this, basically. Okay. So now, we discussed in the previous video how if you've got a sequence of sequences which converge pointwise like this, then it does not necessarily imply that this sequence of sequences converges in the d infinity metric space. Well, the L infinity with d infinity there, that metric space. And we saw that the reason was that if it converged in the d infinity metric space, then there would have to exist some big N, which I could just draw across there. So there would have to exist some point in this sequences, some S big N, let's say, for which if you take any points that's below any term of any of the sequences that is below this line here, then the distance, let's say here, x little n, and it's the ith term of the Sn sequence, then if I take its the modulus of the difference between this term and its corresponding term in this sequence here, so Li, then that will have to be less than epsilon. And we saw in the previous video that having pointwise convergence doesn't imply that you can find a line like this after which all of these, underneath which all of these terms obey that property. What you can do is you can draw little rectangles for each of the term bits. So for each of the columns you can do it. You can find a point after which all of the terms obey that. But basically all of the columns are going to have different values at which it happens, and basically you can't assure that I can find you a line that goes beneath all of them, basically. These might go off and just be on an unbounded set, so you might not be able to find any big N that's greater than all of these. We called them Ni, so N1, N2, N3, etc. Okay, that concept is called uniform convergence. If these sequences viewed as which you can view as functions, converge in that way, i.e., there exists some point after which all of these terms. Let me say it again. Right. Okay. We're now discussing uniform convergence. And basically, what uniform convergence corresponds to in this picture is that for all epsilon greater than 0, there exists a natural number n, which is an element, a big N, which is an element of the natural numbers, such that such that if little n is greater than or equal to big N, it implies that all of these sequences, so for absolutely every single term, all of the terms, for absolutely every single point, 1, 2, 3, 4, 5, if you go beyond that point, if you go to the point, let's say Sn, if you go to that point or beyond that point, so S little n, then absolutely all of the terms are within epsilon of their limit. That is not true for an arbitrary pointwise convergence. So let me say it again, that for absolutely, there exists a point, big N, such that if you go to that sequence, which we can view as a function, so if I draw this sequence, let me draw the picture again, basically. I think I need to. Right, so let's say here we have our limit L. So this is our function L. So here is 1, here is 2, here is 3, here is 4, here is 5, okay? And here is L1, here is L2, L3, L4, etc., L5. So this is the green function. This is what we're saying it converges to. Now, pointwise convergence tells me that for any epsilon I take, so if I take an epsilon ball around L1, so I take this epsilon interval around L1, there should exist a point, there should exist a big N, such that if I go beyond that point in the sequence, so we've got this sequence S1, S2, S3, S4, S5, etc., which is a sequence of functions which are converging down to these points like this. basically what pointwise convergence tells me is that for any epsilon ball I draw around a single point, so I choose my point, my single point 1, I draw an epsilon ball around the limit L1, and I should be able to find you an S big N such that for that point and for all points after it, so for all little Sn after it, the point that 1 is mapped onto, the real number that 1 is mapped onto by these sequences beyond there, is within that epsilon ball. However, if you go to that point, it might not be true, basically, that the if you act Sn on 2, so if you think of Sn as a function mapping the natural numbers onto real lines, Sn is going to map 2 onto a real number as well. If I go to that, if I go beyond big N, then it's not assured that the value that Sn maps 2 onto will be within an epsilon interval of the limit for 2. So basically, that's the difference between pointwise and uniform convergence. Pointwise convergence, and I apologise if you this was not visible. Pointwise convergence says that pick a single natural number and I will be able to find you a big N after which the value, the real number that sequence maps 1 onto is within this interval, this epsilon interval around the L1 limit. Okay, uniform convergence says that for a given epsilon, I can find you a point big N in this sequence for which all of the points are mapped into an epsilon ball around their limits. So draw epsilon balls around absolutely every single one of their limits. If you take a sequence beyond S big N, so an S little n over here, then that I guarantee you, I can find you, basically I guarantee you that sequence will map each and every single natural number into the epsilon ball around the limit point. That is the difference between uniform convergence and pointwise convergence, basically. That if these sequences converge pointwise, it just implies that if you give me an epsilon ball and choose a single point in the natural numbers, I can find you a point in the sequence after which all the sequences after that map that single point, let's say 1, into the epsilon ball around the limit for that point. Uniform convergence says you give me an epsilon, I'll draw epsilon balls around every single limit point. I don't want to say limit point. Every single limit of the sequences for every single point's limit. Let's say every single point's limit. I'll draw an epsilon ball around every single point's limit, and I can guarantee you basically that I will be able to find you a big N such that if I take any sequence bigger or greater than or beyond that sequence, then that's any sequence S little n will map each of these natural numbers into the epsilon ball around the limit for that point. Okay. And the reason that is what this uniform convergence corresponds to convergence of the sequence in the D infinity metric space. Convergence in D infinity. So if you have a sequence of sequences which converges in D infinity, it means that if we think of if we think of all the sequences as being functions mapping the natural numbers onto the real or complex numbers, then that sequence of functions is converging uniformly in this way that I've drawn here, basically. That you can draw an epsilon ball around all of the limits of the points, and find a term in this sequence of sequences such that if you go beyond that term, all of the natural numbers are mapped into their epsilon balls. And the reason that that corresponds to convergence in D infinity is that convergence in D infinity, just go back to the definition of what convergence in D infinity meant. So if we have a sequence S1, S2, S3, S4, etc. in D infinity, so these are all sequences of real or complex numbers in LP, so Sn is an element of LP, L infinity, sorry, not LP. We'll come on to LP, but for now it's just L infinity. Sn is an element of L infinity. Right, so what did it mean for this to converge to some limit L? So we're now doing a convergence in D infinity, so we're supposing it converges to some limit L. In fact, I'm going to give that a different name, because L, I don't want you to get that confused with what we were calling L up here, which was this pointwise limit. So let's call it, let's just call it the sequence M. So M is a sequence of terms, real or complex numbers, M1, M2, M3, etc. Like that, and the meaning of these sequence of sequences converging to M means that for all epsilon greater than 0, there exists a big N, which is an element of the natural numbers, such that if little n is greater than or equal to big N, it implies that the distance, and the distance metric is D infinity this time, so the distance infinity between the sequence, that's the term of the sequence S little n and M is less than epsilon. But now, so basically what I'm saying is I'm just using the definition of the convergence of a sequence in a metric space. So whatever epsilon you give me, I should be able to find you some S big N, which will obviously depend on epsilon, such that if I take any little s, any term in this sequence beyond that S big N, then the distance of that term of the sequence from our limit of the sequence should be less than epsilon. And remember what this means now. This means Sm, remember, is a sequence of real or complex numbers. So it's a sequence xn1, xn2, xn3, etc. M is also a sequence, which is terms m1, m2, m3, etc. ... And basically, D infinity says the distance in this metric space between this sequence here and this sequence here is defined to be, so D infinity of Sn m should be is equal to the supremum of I is an element of the natural numbers of the modulus of xni minus mi. So basically, take the difference between each of these two terms. That might be a complex number or a real number, but it might be negative if it's a real number. Take its modulus and take the supremum of all of those. So basically the biggest one of all of these, to go over every single term and work out what the supremum of all of them is. Then that should be less than epsilon, which implies that if I choose any specific term, so if I choose this one, for instance, this first term, then that must be less than epsilon. So it implies basically that for all elements of the natural numbers, so for all I is an element of the natural numbers, the distance between the term and the limit mi is less than epsilon, basically. And that also occurs for all n is greater than or equal to big N, because my choice of the Sn was arbitrary. I could have picked any Sn which was greater than or equal to, well, beyond S big N, basically. So I could have picked the little n which was greater than or equal to big N. I chose an arbitrary one of these sequences, and this result was true, so it's true for all of them, basically. Okay, so what I've then done is, if we go back to viewing them by this picture, these sequences as being functions of the natural numbers, then what I've shown you is that for any n is greater than or equal to big N, and for whatever term you like, the distance between that term and mi is less than epsilon. So now, obviously it's confusing because I've labelled all of these. In fact, I'll draw another picture so that we're not moving continuously up and down, and so that I can relabel those points. So here we have 1, 2, 3, 4, 5, etc. Right, now, this sequence that you're converging to, this M sequence, is here, so we'll put those on, M1, M2, M3, M4, M5. The criterion for uniform convergence is, okay, draw epsilon balls around all of those. There should exist a point in this sequence of sequences, so some big N in this sequence of sequences, such that once you're past that point, then those sequences map all of the natural numbers into these epsilon balls around the limit, basically. And that is true because look what we've got here. Just use the big N that came from here, basically. Just use that big N, and if you go beyond that big N, then the distance of a term xni, which is basically xni, if you want to view it as a function, is just what the sequence the nth sequence maps the natural number I onto, the distance between that and mi is less than epsilon, and that's true for all I as an element of the natural numbers. So whatever natural number you plug into this function, it works, and for all sequences greater than or equal to big N, which is exactly what we wanted to prove. We wanted to prove that there was a point in the sequence of sequences such that if you go beyond that point, those sequences map the entire natural numbers into the epsilon ball, an epsilon ball around around the sequence, which is the around the points which the limiting sequence maps the natural numbers onto. So that is just hopefully giving you a bit more intuition into what convergence in D infinity means, and why it's stronger than pointwise convergence, but why you will still converge to exactly what this sequence converges to pointwise. So if you have a sequence which converges uniformly, the limit, it does converge pointwise, and indeed it does converge to what is pointwise limit. However, if you've got a sequence which converges pointwise, it isn't necessarily true that it converges uniformly, and uniform convergence is what we mean when we say convergence in the D infinity metric space. So hopefully that's given you a bit more intuition onto that about this subject.